Good day and welcome to FTM. This is an abbreviated version of another video I made on the same topic. So I'm just going to run through the results. The other one shows you the assumptions and the model. But yeah, I just want to look at a number of simulations I've done using the Ferra model, which is used to simulate virus infections, pandemic virus infections. And let me show you the baseline. So in the baseline, the contact rate is 1. So each person that's infected transmits the disease to one other during a week. Okay, and now in a population of 1 million, this is how the new infections, how the disease spreads through the population. I think peaks in winter. I think it peaks on the 24th of June, when you have about 20 million new infections per week. And then it rapidly dies off. You can see it dies off much faster than it rises here. Although this is huge, this is exponential, this is even faster. The thing basically consumes itself as there's nobody else to infect. Okay. Now let's look at some variations on this topic. So let's do a few simulations with other assumptions. So if we have 20 initial infected, then there's very little change from the baseline. The baseline is this red one. There's your 20 million or 20% of the population that gets infected. Let's say we start with a larger initial group, then this just moves forward. Right? For this one, in the second week, there's 20 infected, and here it starts off with 20 infected. So it's just a small little change, but basically the trajectory is the same thereafter. Now, the contact rate is 1, as I showed you in the baseline. Let's up the contact rate to 2. So you transmit the disease to 2 others during a week. Then this thing changes dramatically. As you can see, it just explodes. However, within a month or so, there's really nobody else to infect, and the thing collapses in on itself. This thing has completely devoured itself, and it comes crashing down as it runs out of people to infect. So this is a wonderfully quick way of getting rid of the diseases. Everybody gets it and develops an immune system against it. Of course, you pay a huge cost here because your medical services are overloaded. Everybody is sick. Okay, so let's try and flatten the curve as everybody tries to do. If the contact rate goes from 1, the contact rate goes to 0.75. So you infect 0.75 people per week, right? 1.5 in 2 weeks. Then it changes from there to there. So we're really getting this peak down, but we're also making it much longer. I mean, here we've got, I don't know, 3 months, whereas here we have month and a half. Okay, let's increase the contact rate a bit more to 0.5. So you really infect 1 person in 2 weeks. Then the thing is so flat you don't see it. Now here at the end, it's maybe 500,000 or so. So the infections here do increase rapidly, and they are high. It's in the thousands. But on this graph, you don't see it. Compared to these ones, it's not noticeable. The problem with this contact rate is that everything happens in the next year. So although you don't see anything here, everything happens in the next year. Okay, so the contact rate makes a big difference, makes a huge difference. I mean, there's not that much difference between these contact rates, and the outcome here is hugely different. So let's try and simulate this contact rate. This contact rate is also not constant. It changes over time. It changes by behavior patterns. Governments are trying to clamp down on this contact rate by locking down economies, as they've just done here. So let's see what the impact of that might be. So what I would do is to add variability. So let me show you an example. Here's an example. Let's use, for example, a Pareto distribution. Now, Pareto distribution as the 80-20. There's an 80-20 type distribution. So although the average is 1, typically you have very few contacts. Very few contacts, but every now and again you have a lot of contacts, where contact rate increases dramatically. Right? So it would be leptokurtic. This would be a very leptokurtic distribution. So what happens now? Let's draw random samples in each week, random draws in each week from the Pareto, and use that to drive the simulation. Let's do that 100 times. So there's 100 simulations here, and the outcomes look like this. As you can see, it's pretty tame. It's pretty tame compared to what we looked at before. Even here, there's, in the worst case outcome, towards the end of the year, you have sort of a 12.5 million new infections per week. So this one has the same average. It's a one person per week contact rate. However, it is extremely flat when compared to the others. So here the simulation is not clamping down on the contact rate. It's just simulating sort of what I would take as normal human behavior. We have a lot of contact with few people, and every now and again you go to the mall or you go to some function and you have a lot of contact. To me, that would be typical, and if you want the typical situation, the thing doesn't explode as in the simulations we looked at earlier. Rather, we have the thing never really getting off the ground. Okay, so let's vary the contact rate a bit more and look at some alternatives. So here I've looked at some alternatives. If you use a uniform distribution, now this one also has a much higher average or mean. So that's pretty similar to the two contact rate of before. There's the baseline again. If I use an exponential distribution, which also is a leptokurtic distribution, then yes, it flattens quite a bit. It does flatten quite a bit, but it spreads out over a much longer time period as well. Right? And there's my Pareto. It gets completely flat on this graph. It just goes nowhere. So it seems normal behavior, leptokurtic type interactions, will not see this thing exploding like we see here in the baseline, which is encouraging. But the problem, like with these lines, is pushed out into the next and the outer years. So with all the lockdowns happening, I hope we can completely destroy this thing. We shouldn't really cut down on the contact rate. We should completely destroy the thing to make these efforts really effective. Otherwise, we're going to have lockdown for a very long time. Well, that's it. I hope you enjoyed this, and please leave comments below. Any of these simulations you can do on FTM, and it's now out in the App Store. Thank you very much. Bye-bye.